Hi, in this lesson I want us to have a look at some more examples of faults to see if we can work out what type of faults we're looking at um, and to see some of the impact that these have in the landscape. For example, here this is an image of the Great Glen, this enormous, very straight valley that cuts from coast to coast in northern Scotland. But more about that later. For this lesson, we're working on pages 8, 9 and 10 of our Theme 13 booklets. Okay then, let's go. Now the first job we need to do is we need to make sure that we've fully answered question 4 on pages 8 and 9 of your booklets. You should have marked in any movement arrows, highlighted fault planes, and worked out the type of faults that are shown in each of these images, and perhaps as well marked in the type of stress, whether it's tension, compression, or shear, that's created each of these faults. If you haven't done that, press pause and have a go at that now. If you have completed all of that, check them through, and then let's see what we've come up with. Okay then, let's see what you've come up with. So this is our first photograph. Let's highlight the fault plane. We can see there where the rocks have been displaced. If I mark in some movement arrows, so you can see there the footwall of this fault is the down throw. Because the footwall is the down throw, this is the model of the type of fault we're talking about, and it's a reverse fault. So this is a product of crustal compression. In photograph 2, a very obvious fault plane there, where the beds have been displaced. It's a clear white marker bed, which shows us that we have these particular movement arrows. Now in this case, the down throw side here is the hanging wall of the fault. So if the down throw is the hanging wall, our model shows then this is the type of fault we're talking about. So this therefore must be a normal fault. This is the product of crustal tension. Slightly different image now. We've got an image of the surface, some beautifully ploughed fields that have been displaced. So we've actually got a fault plane visible at the surface there, where this break has occurred. We have some movement arrows showing, but these movement arrows we can see must be horizontal. So what we're talking about here is a strike slip fault. And if we model the movement of this with your hands, we can see it's a left lateral strike slip fault, because the left hand side of that fault is the one that's moved closest towards you. In photograph 4, we now start to see multiple fault planes. So we have one there, but we also have another one there. Okay. There's even a smaller one further to the right as well, but that's fine. We've got some movement arrows then for each of these faults. So we can see the block in the middle has moved up. The 2 blocks either side have moved down. So we get a feature that looks a little bit like this. Now, if we look at where the down throw side is, both of the down throws shown here are hanging walls. So both of these faults are normal. This would be formed by crustal tension, and it creates a feature we call a horst, Horst. Photograph 5, again, we've got multiple faults here. Let's just mark in some fault planes. So there's clearly a lot of displacement going on here. So we mark all the arrows on. You will see that these faults all have something in common. In all of these faults, the hanging wall is down thrown. We get a pattern that looks like this, all caused by crustal tension, so these are all normal faults. This is a type of structure we call Horst and Graben. The Graben is the down-faulted block, the Horst is the up-faulted block, and it can create whole landscapes. A lot of the west of America, for example, has what we call a basin and range topography, created by faulting just like this. Perhaps more about that in another lesson. Bit simpler this time. We just have the one fault to mark in for this one. It always amazes me that a lot of these photos of big cliffs with person in for scale, the person never seems to be wearing a helmet, but there we are. We've got our movement arrows there. So the model that reflects this, we've got our down throws there, there's the hanging wall. So this, once again, is a normal fault. In photograph 7, a few more complicated structures here. So we've got a whole series of a couple of major faults here. There are some small ones as well. And again, we've got a down-faulted block here. This is what we'd call well, the faults themselves, of course, are normal faults. The down throw side is the hanging wall. Where we've got two of these coming together, it creates a structure we call a graben, or a rift, all formed by crustal tension. Photograph 8, number of faults in this cliff face. We have one there, one there. Put some movement arrows on these. Again, we see the down throw sides are the hanging wall. So these are normal faults. And there's a whole series of them in line. This is a feature we call step faulting, because the beds, if you like, step down with each fault. This is a product of crustal tension. Photograph 9 shows a much smaller scale fault, but it still works in the same way. So we've got hammer for scale there. There's our fault plane. Put our movement arrows there. This time we can see the down throw side is the footwall. So this is the model that represents what we're looking at. This is a reverse fault, the product of crustal compression. And finally, we have a much bigger fault to look at. This is a satellite image. This is from Southern California. If we look, there's a displacement of beds running along that line there. We see this at the surface. So we've got a movement like that, but that movement is horizontal. So we know it's a strike-slip fault. It's actually a right lateral or a dextral strike-slip fault, because the right-hand side has moved closest to us. And this is the product of shear stress that we see along the San Andreas Fault. Okay, we started this lesson mentioning this feature in Scotland called the Great Glen. There it is. I want us to look a little bit more at the geological evidence for what's going on there. You can see that the geology either side of that line is different. There's also a clear impact of this in the landscape. This is a Google Earth image of Scotland. There are parts of Scotland's geography that are determined by its geology. There are several different examples of this. You can see, for example, the southern edge of the Highlands that I'm indicating with the cursor here. A really obvious feature. But I want us to zoom in on another feature here. If we look, there's a distinctive line cutting right the way across Scotland, from Fort William down here on the west coast of Scotland, all the way over to Inverness here on the east coast. And these distinctive straight lines running through the landscape that we can trace even all the way out to sea here. If we zoom in a little bit, we can start to follow these structures. From the Isle of Lismore, we can follow a surprisingly straight line right the way across the country. Even defining probably the most famous lake in Britain. Here, this is Loch Ness. Extremely long, extremely deep, and surprisingly straight. And it's the straightness of this line that we see continuing even over to the east coast, past the city of Inverness, even defining the coast here of the Black Isle. That we're interested in. This is the feature we call the Great Glen, and there must be a geological reason for it. What could that be? So we've got a number of different pieces of evidence here, from the geology, from the landscape. What I'd like you to do now is have a go at question 5 on page 10 of your booklets. See what you can work out about this area. And as we watch the sunset over the Great Glen, we can see that understanding these faults can tell us a lot about crustal stress that's applied at any one time, but also we can start to look at some bigger impacts on the geology or the landscape of areas even as big as the Scottish Highlands. Next time we need to think about how folds work, but that's for another lesson. I'll see you then.